Hello everyone, I'm Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, I'll be discussing single phase full wave midpoint rectifier with resistive load. And if you see, there is a circuit diagram of single phase full wave midpoint rectifier. And here we will be taking a single center tap transformer where primary of the transformer will be connected to the supply voltage and secondary of the transformer, the center tapping is taken and it is connected to the resistive load such that during the positive half cycle, the polarities will be like this: positive, negative and positive, negative. So when anode of the thyristor 1 is positive with respect to cathode and when the triggering pulse is actually provided, at that instant the thyristor 1 will be short circuited. That means it acts as on switch and it starts conducting current through the load in this direction. Again through load in this direction. So since the current flowing through the load is in this direction, the polarities will be positive, negative, and this is nothing but V0 output voltage. And if you derive the expression for this, see here, this is nothing but Vs. And if you see in the lower half of the circuit, since this is positive, negative, anode of the thyristor 2 is negative with respect to cathode, T2 is actually reverse bias and it is in the off state. It acts as a off switch. T2 will be acting as an off switch and only T1 is forward bias. And so what? Thyristor 1 will be conducting current through the load during the positive half cycle. So now, since thyristor 1 is conducting, let us apply KVL for this particular loop. And since the current initially is striking the positive terminal, let me take it as plus V0 minus Vs. Since this is short circuit, whole is equal to 0. This is for positive half cycle. I'm writing the equation. In that case, we get V0 is equal to Vs. V0 is equal to Vs during the positive half cycle. That means when anode is positive with respect to cathode, thyristor is forward bias, and the moment when we provide triggering pulse, it is short circuited and it conducts current through the load. And at that instant, whatever the supply voltage which we are actually feeding will be appeared across the load, and that is how V0 is equal to Vs during the positive half cycle. And during negative half cycle, the polarities will be negative, positive and negative, positive. And because of which anode is negative with respect to cathode, T1 is reverse bias and it is acting as an off switch. And due to these polarities, see, T2 anode is positive with respect to cathode, and when we provide the triggering pulse, thyristor 1 starts conducting current through the load, and that is how, see, current flows through the load in this direction. Since current is flowing in this direction, plus minus, and this is V0, and then this is Vs. And for the negative half cycle, if you write down the expression, see here, plus V0 minus Vs is equal to 0. In that case, we get V0 is equal to Vs even during the negative half cycle. So that is the reason, in spite of applying AC voltage, the output is DC, since current through the load during the positive half cycle as well as negative half cycle, current through the output is flowing in same direction. That is how we are getting unidirectional output. Alright, so this is V0 is equal to Vs and V0 is equal to Vs during the positive as well as negative half cycles. Let us derive the expression for peak inverse voltage. Let me take this case. In that instant, the expression will be plus V0, again conducting through, minus Vs plus Vd2 is equal to 0, where I am taking V0 as minus Vs So here minus Vs plus Vd2, where Vd2 is equal to 2 Vs, and I am taking Vs as Vm sine omega t, since Vs is equal to Vm sine omega t, where I am taking omega t when sine will be maximum at this instant called pi by 2. Sine 90 is equal to 1. So at that instant, Vd2 is equal to 2V maximum. This is nothing but the peak inverse voltage formula. That is, peak inverse voltage is nothing but the maximum voltage which is appeared across the thyristor during the off state. So that it need to withstand 2 Vm. And let us see the detailed circuit operation along with the waveform for the single phase full wave midpoint rectifier with R load. So here during the positive half cycle, since the polarities are positive, negative, during which, as I told you, anode is positive with respect to cathode, and since thyristor 1 is conducting current through the load in this direction, and this is nothing but a V0 during the positive half cycle. So thyristor 1, immediately when positive half cycle is appeared, T1 is forward bias, but the moment at which we provide the triggering pulse, gate triggering pulse for the thyristor, only then it starts conducting, otherwise no. So that is how thyristor 1 is conducting right from this instant called alpha, from alpha to pi, thyristor 1 is conducting a current through the load, and that is how we are getting the output voltage from alpha to pi. And the moment it reaches pi, what is happening? The negative half cycle has been appeared, and because of which the polarities will be again negative, positive, negative, positive. So due to these polarities, what happens now? Anode is negative with respect to cathode. That is the reason thyristor 1 is reverse bias, or it acts as an off switch. And during the negative half cycle, since anode of the thyristor 2 is positive with respect to cathode, T2 is forward biased and it starts conducting current through the load in this direction. And that is how we are getting the output voltage right from this instant called pi plus alpha to 2 pi. Since T2 is conducting, we are getting output voltage right from pi plus alpha to 2 pi. And at this instant called 2 pi, thyristor 2 will be turned off because the positive half cycle has been appeared, and T1 comes into the conduction state and the cycle repeats. And talking about the output current, see, the moment when thyristor conducting, the current starts flowing through the load right from alpha to pi. Again, at this instant called pi, since thyristor is turned off and it is remained off from pi to pi plus alpha, and the moment it reaches pi plus alpha, here we are providing the triggering pulse for thyristor 2. Here thyristor 1, thyristor 2 and thyristor 1. The moment when we provide the triggering pulse for the already forward biased thyristor 2, at this instant from pi plus alpha, thyristor 2 starts conducting current through the load till 2 pi, and at this instant called 2 pi, thyristor 2 gets turned off since positive half cycle has been appeared and the cycle repeats from 2 pi plus alpha to 3 pi. And this is nothing but the output current. And now let us see the voltage waveforms for thyristor 1 and thyristor 2. And if you see, thyristor 1 is turned off at this instant from 0 to alpha. Since thyristor is off, whatever the source voltage will be appeared across the device during the off state of the device. The off state voltage of the device will be high and it is exactly similar to that of Vs. So that is the reason it will be following the input voltage waveform. That is from 0 to alpha. And the moment it reaches alpha, what is happening? Thyristor 1 has come into the conduction state. So that is how the voltage across this particular device will be almost equal to 0. That is, on-state voltage drop across the device will be appeared during the on state of the thyristor 1. And the moment it reaches pi, again thyristor 1 is off. That is the reason whatever the supply voltage will be appeared across this particular thyristor. And again, now thyristor 2 is conducting. So that is the reason the on-state voltage drop of the device will be appearing across the circuit. And the cycle repeats. So this is the voltage across the thyristor 1 and this is the voltage across the thyristor 2, thyristor 1. Let us now derive the expression for V0 average for single phase full wave midpoint converter. And V0 average, the general formula we have is 1 by pi, 1 by t, 0 to t, V0 of omega t into d omega t, where pi is equal to 1 by pi and it is actually conducting from alpha to pi. We have the waveform and where V0 is equal to Vm sine omega t d omega t, and here Vm constant, bringing it out, Vm by pi, and integration of sine is minus cos omega t and it is conducting from alpha to pi. So Vm by pi minus cos pi, minus of minus plus cos alpha, and here Vm by pi, since cos pi value is minus 1, minus of minus plus 1, 1 plus cos alpha, and this is V0 average for full wave midpoint converter. Similarly, we will derive the expression for V0 RMS. V0 RMS, the general formula we have is 1 by t, 0 to t, V0 square of omega t d omega t, where time period is 1 by pi and it is actually conducting from alpha to pi, where V0 is equal to Vm square sine square omega t d omega t, constant, bringing it out, Vm square by pi, and in order to integrate sine square, we need to write this in terms of 1 minus cos 2 omega t by 2. It is actually conducting from alpha to pi, and this is whole to the power of 1 by 2, not to forget. So here Vm square by 2, bringing it out, 2 pi, and integration of 1 is omega t conducting from alpha to pi, minus integration of cos 2 omega t is sine 2 omega t by 2 within the limits alpha to pi. And here Vm square by 2 pi, substituting the limits, upper limit minus lower limit, that is pi minus alpha minus sine 2 pi by 2 minus of minus plus sine 2 alpha by 2 whole to the power of 1 by 2, where sine 2 pi value is 0, and applying root to this particular term, we get Vm by root 2 pi, and here this is pi minus alpha and this 0 plus sine 2 alpha by 2 whole to the power of 1 by 2. This is a V0 RMS expression for single phase full wave midpoint converter with R load. And in the next lecture, we will be seeing problems on single phase half wave controlled rectifier. Thank you.